we will start looking at unbalanced system performance and how do you analyze that. So we've only talked about balanced systems, balanced three-phase systems so far, right? So and with a balanced three-phase system, I can automatically go and draw a single-phase equivalent circuit, and life is easy and life is nice, right? So I can take my three-phase system and reduce it to something like, as simple as this, right? Whether I have a generator, a transmission line, and a load, for example, right? I can do that for a balanced system. How about if the system is not balanced? If the system is not balanced, one thing I can do is I can solve the full three-phase circuit. I can no longer reduce it to this because I will have a neutral current, right? So this is my three-phase system. This is my three-phase system. If the system is balanced, this neutral current is zero, right? When the neutral current is zero, I can bring this point and this point together. And if I do that, it's like taking this circuit outside by itself, right? This portion, this part of the circuit here, outside. I brought these 2 points, I joined them together, right? So I can solve my single-phase equivalent circuit that way. But if there is current here in the neutral, so an unbalanced case, if x here does not equal x here, this is x1, x2, and x3, and they're all unequal. If they are unequal, what do? You can use your circuits techniques. You can use what you know about circuit analysis, and of course you would have to do 3 loops here and solve your loop equations. Do we agree with that or not? I can do that. I can do my Kirchhoff voltage law around this loop, Kirchhoff voltage law around this loop, Kirchhoff voltage law around this loop, and you will be able to solve your system. No problem. You can do that. You can go that approach. But in this approach, of course, what's happening? You have an interconnection. The different phases are sort of going to be affecting each other. Why? Because this current here is due to what? Is due to current contributions from phase A, as well as from phase B, as well as from phase C, right? The neutral current is the sum of all the currents here, right? So this neutral current is going to be linking all the circuits together, right? So if you want to do Kirchhoff voltage law around the loop, fine, you will have an equation for phase A that includes, components or currents and impedances from phase B and C, right? You don't have a choice because of the fact that you have this neutral current. So, and it's no problem. You can do this for, one source and one load, right? But what if you have, a system with 10,000 nodes and 50 generators and 20,000 customers or 1 million customers? So how do you do this? It's much easier, to do it this way, right? Single-phase equivalent circuit. Even if you're a computer and you want to do this in real time, the number of computations that you will go through here versus the number of computations that you will go through here is very different, right? So people are gonna, computing power is increasing, yes, for sure, and you can solve circuits a lot faster, yes, for sure, but you would always want to solve them as fast as possible, right? So you'd always want to go to and do something as simple as this. That's one reason to do this, right? Another reason, is that people a long time ago, when power system engineering first started, they didn't even have computers. Right? There were no computers to be able to solve these large systems easily, or the computers were a lot slower, right? So people came up with ways to sort of simplify the analysis of a system that is unbalanced using what is called symmetrical components theory. It's a mathematical manipulation of the power system circuit to be able to solve it easily. That's how it started initially. But what we end up with is also some interesting physical intuition. So we will not, fine, it's a mathematical tool that simplifies the analysis. But people can go and say, okay, I don't care, I have a super fast computer. iPad Pro now has a 64-bit processor, right? 64-bit, it's as fast as any desktop computer, as many desktop computers, yeah. Right? But so people can say, I don't care, I'll solve it this way. But there's an additional benefit you get out of symmetrical components theory as well, is that you get some physical intuition about the system's performance. Right? That is not possible when you merely look at a three-phase unbalanced system and just look at the numbers. So you may look at the numbers and see that the currents are unbalanced, okay? But you will not know if this unbalance is due to a increase on the load on one of the phases or two of the phases. You will not know that. You will not know if one of the phases is connected to ground or not through an impedance. Maybe there's a fault. Maybe there's a transmission line, a tower, and a cow is passing by, right? And the sag hit the cow, right? So what you have a short circuit through the cow, burning the cow to ground. But there's an impedance to ground. So one of the phases, fine, it's a joke, but I think it happens. Yeah, I'm sure if you Google search cow dying because of transmission line, you will find burned cow. Okay, I'm recording this, so I'll stop. But this is a single phase to ground fault, right? This will be a single phase to ground fault. One of the phases touched an impedance, and this impedance is connected to ground. So, but it's not, for example, a pure bolted short circuit. We call it a bolted short circuit. Means it's solidly solidly connected to ground through no impedance, basically. So what we will find is that symmetrical components theory allows us to get a feeling of what's happening in the system as well. Okay, so it allows us to solve the system easier. So what I will do with symmetrical components theory, I will take my three-phase system, and I will figure out how to make it look like single-phase circuits, even though it's unbalanced. I will figure out a way to model a generator. I will figure out a way. What do we have? We have a generator, we have a transformer, we have a transmission line, and we have a load, right? We don't have anything else really, right? So I will figure out how to model these components when they are unbalanced, such that I consider the fact that I have neutral currents, right? And in doing that, I will figure out these models or come up with models that will look like the single-phase equivalent circuits that we've been using before, so that I can simplify the analysis and still do it with my hand for a small system quickly, right? Or if you're going to do it with a computer, you can do it with a computer and you can do it a lot quicker, right? So like there's a lot of research going on now on real-time power system simulation. And we bought one, Dr. Haytham has one in his lab, and what you end up happening is you cannot build an infinitely large system. If real-time simulators, what they do is they simulate the system that you have, that you're drawing in the software in real time. So 1 second in the real life would be 1 second on the simulation. So when you do a simulation, if you took 420, you probably played with Simulink, right? If you took Dr. Hazem's class, I'm sure you played with 420, with Simulink, MATLAB Simulink. With MATLAB Simulink in general is not a real-time simulation. So you can simulate a 5-hour process in 1 minute. Or you may be simulating an electrical machine, for example, in another software. You're simulating a half revolution of the electrical of the motor, but you're simulating that in 24 hours. Or you're simulating a chemical process, forget about the electrical engineering, you're simulating a chemical process that takes place in seconds, but you're simulating that on the supercomputer that is 150 clusters, that is I don't know how many, $1 million, $1 million, I don't know how much it costs. And you're simulating something that happens in a microsecond, you're simulating that in 5 days, right? So these simulators are not real time, okay? There's a big push in power system engineering to do real-time simulation. Why? Because now people want to know exactly why, for example, a failure occurred. For you to know exactly why a failure occurred in a power system, when you looked at in chapter 6, power flow, sometimes if you played, open a bigger example, one of the examples that come with the Power World example software, and maybe start opening some circuit breakers. Okay? If you start opening some circuit breakers in the system, you will see that other parts of the system become loaded, right? So if other parts of the system become loaded to the extent that they start failing, right? Which of the circuit breakers opened first to lead to the overload, to lead to the failure, right? All of this stuff has typically not been recorded in a power system. right? Typically, what we've been recording in power system, voltages and currents and angles, etc., but not in real time. If I know this in real time, I can know exactly what's happening in the powers and what caused the failure and what was the exact sequence instead of having to guess, right? So there's always a bigger push to be able to simulate bigger physical systems in real time. So there's a need to be able to simplify calculations, right? So even though computers are fast, we always need to simplify calculations. There's always a better need, and that's why we have research. Yeah, researchers are still working on things like that. Yeah. So that's that's the motivation behind symmetrical components. And of course, we said that it's used for unbalanced systems. So we first have to define unbalanced systems. If I have a fault on a three-phase system, if I have a fault on the generator's terminals, if I have a generator here, and the way I say, for example, I have a fault here on this bus. Okay, on this, on this bus, right, in this substation where this bus bar and maybe the transformer are located, for example, right? I have a fault here. This fault can be what? This can be. I have three phases inside. This is a single line diagram representation of a three-phase system, right? This fault can be all three phases touching each other, right? For example, some company was digging around the substation, and they sort of, while they're digging, they accidentally cut the insulation on the cables and joined all the cables together, for example, right? This is one type of fault. Or they can all three be connected, shorted together, and they can be on the ground as well. They can be connected to the ground. Somehow they fell to the ground. For example, the transmission tower fell to the ground somehow, right? Or they can be two phases touching each other, right? Or they can be two phases touching each other and also touching the ground, right? Or they can be one phase touching the ground, or not merely touching. When I say touching the ground, it can be touching the ground through an impedance, right? Because anything has impedance, even a copper bus bar, anything has some sort of impedance. Yeah. So this impedance can be small. I call this the fault impedance, Z fault, right? So these transmission lines or the cables can be connected to ground through a fault impedance, right? So this impedance can be large. For example, in the case of a single phase Z fault, ZF here being large, it's probably not a fault. It's probably a bigger load than usual, for example. So if I have a three-phase transformer feeding the three rooms here on this floor, and there's only a lecture in this room, what is the current? And I took one phase to this room, one phase to the next room, one phase to the next room. So I have a three-phase. So this is my transformer. These are my transformer terminals, three terminals, and my neutral. This is A, B, C, and neutral. I connected this to one room between. Remember, everything we have here is between live and neutral, right? Live and neutral, and of course I have a ground connection. I will talk about grounds a lot in the next chapter. But I have everything between the live and neutral. So this is one room, another room, a third room. If only one of these rooms is operational, the other two rooms are like an open circuit, right? And this room is the only one that's consuming current. So is this system operating as a balanced system or unbalanced? Yes? Unbalanced, right? Only one phase has some current. The other two phases have, ideally zero, for example, right? So it's an unbalanced system. So an example of a, unbalanced condition is very simple. A single phase load placed on a three-phase system. That's an unbalanced system. It can be a load or it can be a fault, actually. This load can, be smaller impedance or higher current, smaller impedance or higher current, all the way to zero impedance, right? Zero impedance would be a short circuit. Somebody took a copper bar here and connected the live and the neutral together. This is a short circuit, right? This is one kind of unbalance. A load on one of the phases is one kind of unbalance. A load on two of the phases, not the third one, is another kind of unbalance. basically, anytime that the currents are different between the three phases, you have an unbalance. And these are the main kinds. So it's either a three-phase balanced fault, and whether this or this happen is the same. Why is that? If I have my generator here, my three-phase terminals of the generator, another generator, three-phase terminals. If I have a short circuit across the three terminals, or if I have a short circuit and I've connected this to ground, for example, right? And I've connected, for example, this is my chassis of this transformer or generator is connected to ground, right? What current is going to flow here? What current is going to flow here? The sum, right? Is this a balanced fault or not? What is the sum? What is the sum in this case? I have a generator. I have a voltage, three phase voltages here. This is my generator, represented as three-phase voltages, and I have a short circuit here, right? This is what this is representing, right? So the current here and the current here and the current here, are they different? Assuming I have, this is the cable resistance, for example, cable resistance, R, R, R. What is the current in each of these phases? The same. So they will sum up to what at this node? This is Kirchhoff current law at this node. If you do KCL at this node, what is the current that will come out? If I connect this to ground. If these are the same, but they are phase shifted by 120 degrees. Remember, these are three-phase voltages that are phase shifted by 120 degrees. So the currents here are equal, but are phase shifted by 120 degrees. So the current that's flowing here will be 0. There will be no current. So in a three-phase balanced fault, there is no neutral current. So that is the topic of chapter 7. Remember, I skipped and went to chapter 8 right away. So chapter 7 is what we covered now in 5 minutes, except that they cover problems on it. I will give you homework problems on chapter 7. But basically what chapter 7 deals with is a three-phase fault, a balanced fault. So there are two types of faults. There are balanced faults and unbalanced faults. Balanced faults are three-phase faults. It doesn't matter if I have a short circuit here on the three terminals, or if I have a short circuit on the three terminals, I'm also connected to ground. It does not matter because no current is going to flow to the ground. No current will flow in the neutral to the ground point potential because it's a balanced fault, right? So how would you analyze a balanced fault? Since my currents are balanced, then it's a three-phase balanced system. So I can draw my single-phase equivalent circuit. So it's what we've done before, except that I will here's my line impedance. And instead of putting a large load like we used to, I will have a small short circuit here. That's it. That's the only difference. Or I will have a smaller impedance here, for example. Right? So what will that have? What will that do? That will cause larger currents to flow. I mean, here I have a circuit where I have an impedance and a circuit where there's a short circuit across this impedance. The current here versus the current here. This will be much more. Right? You've removed this impedance. There's less impedance for the current to flow in this circuit. Right? So this will be fault current in this case, I fault. So chapter 7 was about three-phase balanced faults. So it's nothing but what we've done before, but instead of putting a load, we will typically put a very low impedance or put a zero impedance. Right? So that's really chapter 7. So and that is only one of the types of faults that we cover, right? So three phases shorted, or three phases shorted connected to ground. So this is the only type of balanced fault there is. The other types of faults that we talked about were two phases shorted, or two phases shorted and then connected to ground through an impedance or without, right? If without an impedance, it's called a bolted short circuit. If it's with an impedance, it's an impedance, fault through an impedance. We just call it that. And then The other type is single phase to ground fault. This is my Z fault. This Z fault, the fault impedance can be small or big, right? So if it's a bolted single phase to ground fault, the impedance is 0. If it's not, it has some impedance value, right? So these are the types of faults. This is chapter 7, and that's basically you do the same thing as balanced circuit analysis, single phase equivalent circuit, and you solve it the same way we've been doing before. These you don't know how to do yet, and we will learn how to do them in this chapter. Okay. The most common type of fault is this, the single phase to ground fault. This is the most common type of fault in a power system. It's not, typically, do you think something like that would happen on the transmission lines? It would? The probability of it happening on the transmission line is very slim. I mean, it would have to mean that, because remember, at the transmission level, we don't even have the neutral wire going, passing through. We really have the 3 phases only, right? So the tower is grounded. So if something like that happened, it means that actually one of the transmission cables hit the tower, fell and hit the tower, for example, right? Which is, or swayed enough so that the insulator broke and hit the tower, right? So, it may happen, but of course I think the probability is very low there. The probability of it happening, when people are doing a construction project or a building project or, in your home, that's very common, right? It's very, very common to happen. So it's not, it's the most common type of power system fault, yeah. So we will have to figure out how to deal with that because it causes an unbalanced system and we cannot draw a single phase equivalent circuit. So we want to come up with representations for the generators, transformers, transmission lines, and loads that allow us to deal with that, with these conditions, and allow us to draw something similar to a single phase equivalent circuit. That is chapter 8. That's the theory. And then what chapter 9 does, so I'm doing 3 chapters together, right? So what we do in chapter 9 is after we've come up with this new single phase equivalent circuit that we will draw in this chapter, what we will do is solve it in chapter 9. Right? So we will come up with a new simplified circuit that you can easily solve with your hand. And in chapter 9, we will figure out how to actually solve it based on the type of fault. Because solving it, there will be different methods to solve it based on the type of fault. So in chapter 8, we will only figure out how to represent the components or build the circuit. That instead of the single phase equivalent circuit, we will build something else like the single phase equivalent circuit. But in chapter 9, we will say, okay, I will tell you, if it's a single phase to ground fault, okay, this is how you solve it. Take your original circuit that we came up with in chapter 8 and then solve it in a certain way because it's a single line to ground fault. If it's a line-to-line fault, okay, take your take your circuit that you developed in chapter 8 and solve it this way because it's a line-to-line fault, or solve it another way because it's a line-to-line to ground fault, right? So that's these 3 chapters together. Okay, so we'll get started because we're running late. We want to finish another chapter 10 and 12. I'm just kidding. So, okay, so I'm not going to go through this. Okay, so symmetrical components. What symmetrical components theory basically tells us is, if, that's the idea behind it is the following. Anytime I have an unbalanced voltage or current, meaning I have an unbalanced, either voltage source or an impedance in my system, I can take the corresponding voltage and current waveforms and chop them up into 3 different kinds, right? So I can chop them up into what is called a positive sequence, and a negative sequence, and a 0 sequence. So what does this mean? If this is VA, VB, VC, my phase voltages or currents, right? This is I or V, does not matter, right? These look balanced, right? They're 120 degrees apart, and they look equal. What did we call those previously? We sort of gave them a name, right? I said that if I stand here and these rotate and I see A, then B, then C, we gave this a name. What did we call those? Positive sequence. We call those positive sequence. These positive sequence voltages or currents were three-phase voltages or currents that were 120 degrees apart and were equal in magnitude. How about what did we say if the sequence was a bit reversed? So this was IA, and this was IC, and this was IB, and I was standing here, looking at them rotate. This was called, what did we call this when we were looking at the transformer connections? Negative sequence. So we call this positive sequence, and we call this negative sequence. Negative sequence was what? These were still three-phase balanced currents or voltages. So all the magnitudes were the same, and the phase shifts were 120 degrees still. So this was called, we call this positive sequence, and we call this negative sequence, right? And in that case, what did I tell you this? How did I tell you this would happen? This I said would happen, for example, if I flip two terminals of the three-phase system. It would. So this is physically what would happen if I flipped two terminals of the three-phase system. How about if I tell you a system can have both of them at the same time? Right? If I tell you that. But I tell you that they can be both present at the same time, but different magnitudes. So this, the positive sequence, for example, we have a magnitude of 10. And they're all balanced. Remember, this positive sequence is a balanced three-phase system. So this is IA is 10, IB is 10, IC is 10. And the negative sequence is 0.1. Right? Can you imagine something like that? It's like doing what? It's like putting two sources in series on phase A, two sources in series on phase B, right? Two sources in series on phase C, and then, but this one, the phase shift here is 0, and then it's a large magnitude, and then the phase shift here is different, 120 degrees. Doesn't matter. I can do anything. I can put two sources in series, right? I can put another source here, your smaller magnitude and different phase shift, right? And what will be the voltage at the terminals here of phase A? What will be the voltage here between phase A and neutral? Come on. It will be the sum. I mean, just a series sum of the two sources, right? So this you can actually emulate this in practice, right? So what do you think this would do to a motor, for example? If you based on what you know from 338, if you apply this to a motor's terminals, it will spin in a certain way. How about if you apply only negative sequence? What did we say will happen, or what did Dr. Haytham say will happen to the motor? To spin in the opposite direction. So now, what do you think will happen if I apply both, but one is much more significant than the other? Torque components in the motor are due to the flux components in the air gap. Flux components are due to the currents and voltages that you apply on the terminals of the motor. So, which means that you will have components of flux due to this source, and components of flux and current due to this source. It's superposition. But what will that do to the motor? It's like again at the end we want to produce torque. I don't think it will slow it down because at the end of the day to have the same frequency. Typically, frequency is what is proportional to speed, right? Torque is what is proportional to the flux in the gap. And the flux in the gap is typically proportional to V over F, right? So this V now I've added flux components due to a positive sequence and flux components due to a negative sequence at the same time. So which means that I will have less torque at the output because I have torque in one. Remember, the motor spinning in one direction means there's force in one direction. Motor spinning the other direction means there's force in the other direction. If they have a conductor and force with force on it, and this force moves the conductor, that means there's torque applied, right? So which means I have torque components in one direction and torque components in the other direction. What will that do to the output torque on the motor shaft? It will be the sum. It will decrease the amount of motor torque on the shaft. It will decrease the motor torque on the shaft, but the current that produced the positive torque will be there. The current that produced the negative torque will be there. So I actually have more current, but I have less torque. What does that do to the motor? Any machine, if you have more current but less torque than what you're supposed to get, will just heat it up. right there. I mean, you're losing torque density, and you would be, of course, losing efficiency because you calculate the amount of current coming in as well, right? So these machines will heat up. So anytime your machines are operating with an unbalanced power supply, they will be heating up. Harmonics cause unbalance. Failures in your system will cause unbalance. So you cannot run machines unbalanced unless unless you've rated them thermally to make sure that you can tolerate some unbalance, right? So that's why, for example, if you get these generators, these mobile generators, if you feed a load, you have to make sure that these mobile generators, if it's a three-phase generator, it's going to be feeding a balanced load. Otherwise, if it's not, you cannot just feed with these mobile generators, feed one of the phases only, because it will heat up. It's useless, right? And you're just burning fuel. Okay, so we sort of see how positive sequence is generated and how negative sequence is generated. But we don't know how to take and we see, okay, that I can put them in series. And now I will show you how to take any unbalanced, and now, okay, if I put them in series, I look at the voltage here. The voltage here versus, this will be VA. VA versus VB versus VC will now not be, will they be balanced? They will not be balanced. They will not. I mean, you have some VA now that is not necessarily balanced, not equal to VB, not equal to VC. I mean, it's we will see that mathematically. I will show you that the symmetrical components theory will allow us now to take any system that is unbalanced. So if I have an unbalanced system, so this is VA and this is VB, this is VC. For example, this is VA, VB, and VC. What symmetrical component, or IA, IB, and IC. And these can be, magnitudes can be different, or magnitudes can be the same, but angles can be not 120. Maybe this is 120, and maybe this is like, I don't know, 100, and maybe this is 150, 140, right? So it's the unbalance is either magnitudes are unbalanced, or phase is not 120 degrees between the components, because if you have three currents equal in magnitude, but the phase shift between them is not 120 degrees, and you sum them up at a node, are they going to sum to zero? They will not sum to zero. They will only sum to zero if the magnitudes are equal and the phase angles are 120 degrees apart. If that's not the case, they will not sum to zero, and you will have some neutral current, right? So anytime you have an unbalanced system, what symmetrical components theory tells us is that I can take this unbalanced system, voltages or currents, and chop it up into three different components. They can all be there, or some of them can be there, or maybe one, or maybe two. If one of them is there, then we actually have a balanced system. If we only have a positive sequence, or we only have a negative sequence, then we have a balanced system, right? If I have a three-phase power supply that's balanced, and I apply it to a motor, I'm applying positive sequence, right? In that case, I only have one of these components available. It will be a balanced system. If I have more than one of these components available when I apply the symmetrical components theory, it means I have an unbalanced system. I can have two of these components available, or I can have three of these components available, right? And whether I have two or three will give us some physical intuition about the system. It will tell us, you will look at numbers, you will look at the positive sequence, negative sequence, and zero sequence values, and you will know that, okay, there's a cable connected to ground somewhere. You will know by looking at the numbers. You will know that there's an unbalance, but the system, this unbalance is caused by two phases touching each other. You will know that by understanding what symmetrical components theory provides. Right? So that's the objective of this symmetrical components theory chapter. Yeah. So how do you chop? So the positive sequence components are equal in magnitude. They're a positive set of components, and they are 120 degree apart for voltages and currents. Negative sequence, same thing, but this is A, B, C. This is A, C, B. How about the zero sequence components? Zero sequence components are also equal in magnitude, so this is A, but they are all in phase, B and C. Remember when I was talking about the delta, the current in the delta? Remember at some point I talked about the current in the delta, and I said that, let's assume that we have, the delta, sorry, a delta here with impedances and I have loads, three-phase load connected to the delta. What did we say here? I said that there will be current, of course, flowing in these loads, but there will also be, if you do Kirchhoff voltage law around this loop, it's this voltage plus this voltage source plus this voltage source. They're all in the same direction, right? They're all in phase, right? These DC sources are in phase. I can make them AC sources. Does not matter. I can make them AC sources in phase. DC sources is easier to visualize, right? If these DC sources are in phase, so what is the voltage that is going to drive current in this loop? This voltage plus this voltage plus this voltage, and the current will be equal to the 3 voltages divided by these 3 resistors, right? That will be the current that's flowing inside this loop. This is from circuit analysis. So these components of voltages are in phase, and they are called zero sequence components. And I also drew the 3-phase third harmonic in a 3-phase system. If you remember, I drew, if this was VA at 50 hertz, and VB at 50 hertz was 120 degrees away, right? And then I drew the third harmonic for phase A. So this happened 1, 2, 3, 1, 2, 3. So this is the third harmonic for phase A. 3A. So this is the third harmonic for phase A. Was 3 times the frequency of phase A voltage, but in phase with phase A. How about the third harmonic for phase B? How did we draw it? It had to be in phase with phase B, and it's 3 times the frequency of phase B. So it's also going to be, I didn't draw this nicely. I only drew 2 here, guys. Right? I messed up here. So. See, 1, 2, 3 times in the same half cycle, and then 1, 2, 3. I didn't draw it. I have to draw to scale. I didn't draw it to scale. Okay, forget about my drawing to scale. But the idea. Let me try to draw it to scale. The third harmonic for phase A will be this. This is A, and this is third harmonic for phase A. How about B? B will be 120 degrees. We start 120 degrees away, right? So this is, if this is 180, then this is 120, right? These are 3, 1, 2, 3. They're supposed to be equal. I didn't draw them as nice, but this point is 120. If this point is 120, that means this is where point phase B starts, and this will be 160, 120, 180 degrees. So this phase B will be here until here. So what is the third harmonic of phase B going to look like? This is phase B. The third harmonic of phase B will also be in phase with phase B, and will be 3 times the frequency of phase B. The third harmonic for phase A and the third harmonic for phase B are in phase. Right? They are in phase with each other. If they are in phase with each other, what will they do if they are inside the delta that we're talking about? These are in phase. All of them are in phase. It's like the DC sources. They will cause current to circulate inside the delta. That's what we were talking about back then when we were talking about the delta and circulating current inside the delta, or trapping the third harmonic current inside the delta. Anytime you have a zero sequence component, zero sequence components are components that are equal in magnitude and phase. So they are equal in magnitude and phase. So DC is equal to magnitude and phase. This third harmonic is equal in magnitude and phase. in a three-phase system. Fifth harmonic would be equal in magnitude and phase in a five-phase system, right? So it's different in different number of phases, but this is what's called zero sequence. Zero sequence are just components that are equal in magnitude and phase. And what they do here is, in the delta they will add up. What do you think they do in a star? I have zero sequence here, zero sequence here, zero sequence here. This is IA, zero sequence. IB, zero sequence. IC, zero sequence. The zero sequence current is flowing in this resistor, this one, and this one. What is the current flowing out? These are all coming in, and this is coming out. So the sum of everything coming into the node is equal to whatever is coming out of the node, right? Kirchhoff current law. So if I add IA plus IB plus IC, zero sequence. IA, zero sequence. Plus IB, zero sequence. Plus IC, zero sequence. What would I get? What did we say about zero sequence? They are equal in magnitude and phase. So I can say they're all equal to IA, for example. So what do I get? Do I get zero? I do not get zero. There will be, this is not zero. This is not zero. So zero sequence components actually are what cause neutral current to flow. Right? So anytime you have neutral current flowing, you will know that there's zero sequence component happening. There's zero sequence component in your circuit. And if neutral current is flowing, it means that there is a connection between the neutral point and ground. We either have a three-phase circuit without a neutral, connected. This is my source and my load, for example. Three-phase source, three-phase load. I don't have a neutral connect. For example, you can have that. Or the other way is you have these neutrals connected, and these neutrals can be connected and connected to the ground somehow. So we would typically have a connection to ground somewhere, because if there's no connection to ground, and these are far away from each other. So this is a source that is far away from your load. Typically we would have what? Typically we would connect to ground here, connect to ground here. This would put this potential and this point at the same potential. So if there is an unbalance, there will be neutral current flowing, from your source, through the load, through the neutral, through the ground, back to the neutral of your source, right? So canvas, white background, right? If there's an unbalance. If these are unbalanced, the resistors are unbalanced, R2, R2, and R2. These are unbalanced resistors. Even if the voltages are balanced, are equal and 120 degrees apart, then the currents will be unbalanced because the resistors are unbalanced, right? You have to have a balanced source and a balanced load to have a balanced system. If they are not, then the currents will be unbalanced. The currents are unbalanced. What does that mean about this connection? That we will have neutral current. If these currents are unbalanced, that means the sum will not equal to zero, and I will have current flowing in my neutral. Right? Typically, these circuits can be far away from each other. So the way we would typically connect them is actually, if they're far away from each other, we would typically connect them through the ground connection, through a ground mat. So here in this building, no, we would have this neutral point here that we have in this room connected to the neutral point of the transformer. Right? So think of this as this room, these three rooms. These three loads are the three rooms, the three lecture halls here. We would typically have the neutral point connected back to the neutral point of the transformer. So think of this as a transformer, for example. Okay? And if I detect current flowing in my neutral, I know that I have an unbalanced system, and I know that I have an unbalanced system if I have current flowing in my neutral lane. And I can do that by looking at zero sequence. quantities. If I have I0 not equal to 0, right, after I look at how to take from my phase quantities and calculate my zero sequence quantities, actually we did that for the zero sequence. We said that I0, the zero sequence, the IA plus IB plus IC, the zero sequence components of the three values of current is equal to 3 times, IA, or that is equal to the neutral current, right? So the neutral current is equal to 3 times the zero sequence component. So if I have a zero sequence component, that means the neutral current is equal to that zero sequence component divided by 3. If I have neutral current, that means if I take that neutral current multiplied by, if I have to take that neutral current divided by 3, I will end up with my zero sequence component. Do you see where I calculated my zero sequence component from? Right. So you can these sequence components are not something you can measure. Right. They are a manipulation. Right. They're mathematical manipulation of the variables that you're measuring. What are the variables that you're measuring in this system? IA, IB, and IC, and the neutral current. Right? I'm measuring IA, IB, and IC are my neutral current. I'm measuring VA, VB, and VC, and the line voltages, for example. Right? Do I have, if I find these unbalanced, A, B, and C, what is can I measure I said that if a system is unbalanced, I can take it and chop it up into positive sequence, negative sequence, and zero sequence components. How do you do that? We need a mathematical manipulation to allow us to do that. I cannot go and measure positive sequence, negative sequence, and zero sequence for an unbalanced system. You can measure phase quantities and apply a mathematical manipulation to come up with positive sequence, negative sequence, zero sequence representations of the system. Okay, so they are representations of the system. And if I have positive sequence, negative sequence, zero sequence, representations of voltages and currents in a system, what do you think I can also relate these two with? If I have positive sequence voltages, positive sequence voltages and currents, negative sequence voltages and currents, zero sequence voltages and currents. What do I know? What is the only equation we have in electrical engineering? Ohm's law. So Ohm's law says V equals IZ. Right? So this is the only thing we have in electrical engineering. Right? So if I have V0, I0, that means there is a Z0. If I have V positive, V negative, that means there's a Z negative. Right? So which means that what we're going to lead to, what we're going to come up with is 3 different representations of a 3-phase system. So we're going to come up with what we call sequence circuits. These sequence circuits will be simple single-phase circuits like we know how to solve that will represent an unbalanced system. Okay, that's the objective. I mean, all of this I'm talking about the objective of the chapter. But is it clear? Is it clear what we're trying to do? So now we just need to figure out this. What does this mathematical manipulation look like, right? And this mathematical manipulation is something that was that people came up with in the 1918s. So it's a very old mathematical manipulation. So it's a very old theory. It's called symmetrical components theory. And what symmetrical components theory tells us is I can take any unbalanced system and, as we said, chop it up into a positive sequence subsystem, a negative sequence subsystem, and a zero sequence subsystem, or representation. So I can take a generator. If the generator is unbalanced, I can take this generator and chop it up into a representation for that generator in a positive sequence circuit, a negative sequence circuit, and a zero sequence circuit. And at the end, when I have my positive, negative, and zero sequence components of phase A, for example, this is my phase A positive sequence. This is my phase A negative sequence. This is my phase A zero sequence, right? These are my zero sequence, my 3 sequence components for phase A. What does the voltage of phase A look like? It's the sum of the positive sequence component, the negative sequence component, and the zero sequence component of phase A. What does the negative sequence component, what does phase B look like? the sum of the 3 sequence components of phase B. What does phase C look like? The sum of its sequence components, right? So here, this is phase B that I'm measuring. This is the only thing you can measure is the real phase quantities. I'm measuring phase B. This is phase B. Phase B is made up of its sequence components if the system is unbalanced. So it means that I go here and look at my positive sequence for phase B. Positive sequence for phase B is this one. So I take this one here, my positive sequence component for phase B. Then the negative sequence component for phase B, it happens to be here. Again, they can have different phase angles versus these, right? These don't have to have, they don't have to start at the same reference because they will have different impedances, right? We will have different circuits that we are going to be dealing with, right? So in the general case, they are not in phase, right? So I will take the negative sequence component of phase B here, and the zero sequence component of phase B. So they actually added the zero sequence plus positive sequence plus negative sequence component, and they came up with phase B. Right? It's the vector sum of the zero sequence, positive sequence, and negative sequence. And in the book, we can either use 0, 1, 2, or 0, positive, and negative. Okay, so the book sometimes uses this, sometimes I use sometimes this and that. Okay? So I always refer. So 1 is positive, 2 is negative. Right? Same thing for phase A, which is here, composed of its sequence components, and same thing for phase C, which is here, composed of its sequence components. Right? So this is my phase C for that I'm measuring. C. Phase B that I'm measuring seems to be here, a little bit bigger. Phase A that I'm measuring is somewhere here, and a lot bigger. Obviously, this is an unbalanced system. Right? This is a three-phase unbalanced system. So how do I go now from these to these using symmetrical components theory? There will be, we will use what is called the sequence matrix. So we will relate the phase quantities, so the phase quantities and the sequence quantities. Okay, so we will have a vector of phase quantities and a vector of sequence quantities, right? We're trying to relate my phase quantities VA and VB and VC to their corresponding sequence quantities. So what is the relationship between them? The relationship between them is this sequence matrix. So VA is composed of V0 plus V1 plus V2. And VB is composed of V0, A squared, V1. And remember here they refer to V1 as the positive sequence of phase A. So here I think they mentioned that. So for simplicity, the subscript A is dropped to denote these sequence quantities. Remember that these are the positive sequence and negative sequence components are balanced systems, right? So what is the relationship between the phase A positive sequence and phase B positive sequence? They're the same magnitude, but 120 degrees apart. And phase C, same magnitude, but 120 degrees apart. So can I write phase C positive sequence as phase A positive sequence, but with a shift of minus 240 or 120? I can do that. Instead of having to write A positive sequence, B positive sequence, and C positive sequence, right? I can write C positive sequence in terms of A positive sequence, or B positive sequence in terms of A positive sequence, right? It's just equal to phase A positive sequence. Phase B here, positive sequence will be equal to phase A positive sequence, shifted by 240 degrees, right? So let's look at phase B, for example. Phase B will be equal to the zero sequence component of phase B. That's fine, because the zero sequence components are all in phase, so it doesn't matter. How about, so we said that the phase B is equal to its positive sequence plus its negative sequence plus its zero sequence. So what is its positive sequence? Its positive sequence is equal to phase A positive sequence, phase shifted by 240 degrees. So A will be the one angle 120 degrees. You know that will A will stand for that. So if A squared will mean it's a phase shift of 240 degrees, right? So this means that A squared V1 is basically the positive sequence of phase A, phase shifted by 240 degrees. And then, so I have to add the zero sequence of phase B, positive sequence of phase B, negative sequence of phase B. What does a negative sequence of phase B equal? The negative sequence of phase B is equal to the positive, is equal to the negative sequence of phase A, phase shifted by 120 degrees. Right? So it's A times V2. A times V2. Okay, so it's still, I'm adding up the positive, the zero, the positive and negative sequence components for each of the phases. I'm just representing them all in terms of one variable for simplicity, which is the phase A variable for simplicity. Okay, so that's where this matrix comes from. Right? And it just comes from the fact that we agreed that if a voltage is unbalanced, it will contain zero positive and negative sequence components, and the full voltage is equal to the sum of them for each of the phases. And that's, so we represented that using these phase shifts, and we took that and represented it as the matrix. And we will call this the sequence matrix. Yes?
So you're representing VA, VB, and VC in terms of VA, right? Of the
In terms of the zero sequence, positive sequence, and negative sequence components of phase A, of one phase. Yes. Okay. So now if I have my phase quantities, I multiply by A inverse. I call this my sequence matrix. This is A. I'll call this matrix A later in the next slide. If I pre-multiply by A inverse and pre-multiply by A inverse, I can do what? I can calculate my sequence quantities from my phase quantities, right? Because again, I'm measuring phase quantities, right? I'm not measuring sequence quantities. So I can only measure phase quantities. But I typically want to know what the sequence quantities are, because if the zero sequence current is zero, what does that mean? Based on our discussion earlier. If my zero sequence component is zero, what does that mean about neutral current? There is no neutral current, right? So there is no neutral current, but the system is unbalanced because I have negative sequence. What does that mean? It means that the fault that I have is not causing current to flow in the neutral, so it's not going to be a fault connected to ground. There's no connection. There's no fault. You know, it can be a line-to-line fault, but no connection to ground. We said that three-phase balance faults, we will not discuss them. That's chapter 7. We know how to do that. Unbalanced faults are either going to be line-to-line faults or line-to-line to ground type faults, or single-phase faults to ground. Single-phase to ground means that current is flowing from my phase to the neutral. Double line means what? Is there any current? I mean, double line means I have my generator. This is my source, and I have these two connected, and I have this one here. Let's say not connected. What will happen to? What does Kirchhoff current law tell us about the relationship between these two currents? Yeah, they're equal and opposite. These currents will be equal and opposite. And if I have no current flowing here, right, then I don't have any current flowing in the neutral. This is 0, and this one is equal to this one. This is 0. This is current here is 0, for example. It's not connected. There's no connection here. And this current is equal to this current and opposite in magnitude. So what is the current flowing here? Yeah, this is I and this is I, equal and opposite, 180 degrees opposite of each other, right? This is coming here, so this is equal to this, but with a negative sign. So this is equal to this, but with this is I, this is minus I. So what is this equal to? This is coming, all of these are coming out of the node, they will sum to 0. But this and this are equal to 0, are equal to each other and opposite, which means that there is no neutral current. Right? So if there is no neutral current, that means that the zero sequence component is 0, because remember we said that the zero sequence component is equal to 3 times what? We said that 3 times the zero sequence component, 3 times is equal to the neutral current. Right? So if I have no zero sequence component, if I0 is equal to 0, or if I neutral is equal to 0, what does that mean about my zero sequence component? It's equal to 0, right? So if I am measuring my phase quantities and I calculated my sequence quantities, my phase quantities will give some measurement. They will give some measurement, and these measurements will be unbalanced, right? If they give some measurements that are unbalanced, but you then calculate your sequence quantities, you find a value for V0, you find the value for V1, and you find the value for V2. What will that mean? It means that the system is unbalanced, and if I have a component for V0, it means that if there's a V0, that means that there is an I0. I0 means that there is neutral current. Neutral current, that means that there is something connected to the ground. Right? It's either going to be the line-to-line to ground fault or the single phase to ground fault. It's one of these two. There will be something else that will help us differentiate between them. If I find that my positive and negative sequence components of current are equal and opposite, I will know that it's a line-to-line fault. Line-to-line to ground fault, sorry. We will differentiate between them, when we look at the numbers in more detail. But what I'm trying to say is that these, at least for now, for the zero sequence, we have an appreciation for the fact that if I have zero sequence, that means that there is something flowing in my neutral. If I don't have zero sequence, there's nothing flowing in my neutral. If there's nothing flowing in my neutral, what type of fault is it? It's either going to be a line-to-line fault, or that's it. That's the only option. If the zero sequence component is 0, that means I don't have anything connected to ground. There's nothing connected to ground. There's nothing flowing in my neutral. This table is general. So this is what I was just saying here about pre-multiplying by A inverse. So again, we call this A the sequence matrix, and the sequence matrix relates the phase quantities with the sequence quantities. Right? So if I pre-multiply by A inverse, I can calculate my sequence quantities from my phase quantities. And this applies for voltages and currents. Right? Here all we did was pre-multiply by A inverse. So these are the sequence quantities in terms of the phase quantities. So you would measure your phase quantities and calculate your corresponding sequence quantities and then come up with intuitions based on that. Yes?
So positive sequence is always balanced?
Positive sequence is balanced. Negative sequence is balanced. Zero sequence, equal in magnitude. So they're all balanced. But the positive and negative are also 120 degrees apart. The zero sequence, they are equal in magnitude, but the phase, they're equal to magnitude and phase. So, but the positive and negative sequence are balanced. So when we come up with a positive sequence circuit, we know how to solve balanced circuits. It's similar to what we've come up with before.
Right, because you mentioned that in the case of zero sequence, we always have neutral current, and the only alternative when you don't have neutral current and the system is unbalanced is when you have a line-to-line fault. So what is that condition for having a line-to-line fault? Because it's not a positive sequence, it's not a negative sequence.
No, it will have. I'm not saying it will have some positive. Okay, line-to-line faults. Okay, in general, you will have, if the system is balanced, you will only have positive sequence or only have negative sequence, right? Depending on the way you've connected your system. If your system is unbalanced, you can have positive and negative sequence, or positive, negative, and 0, or you can have negative and 0. Right? You can have positive and 0, meaning your system has a lot of positive sequence, but there is some connection to ground. Right? That means there is some current flowing in the neutral. But you can also have the same condition, but with a negative case. So you can have negative sequence and zero sequence present. It means you have an unbalance. Your sequence, your wires are connected in a certain way, and that there is some neutral current flowing in the circuit. You can have positive sequence and negative sequence, which this probably means, and no zero sequence. This still means you have an unbalance, because balance means you only have positive or negative. If you have positive and negative, it means you have some unbalance as well. But this unbalance, since my zero sequence is zero, it means that there's no current flowing in my neutral. If there's no current flowing in my neutral, it probably means that I may be overloading two phases. Overloading or short-circuiting, I mean, it's the same, right? So we'll stop here. We'll continue next time.